Hi everyone, Eddie is here. The focus of today's tutorial is going to be to show you how you can quantify the number of bacterial cells found in your Salmonella inversion assay and to see how you can make some pretty pictures. So let's start by importing some pictures into our ImageJ. So let's say I want to analyze this picture, so I carry it into this feature software, and this is what the window looks like. So I'm going to view them as a hyperstack, and now I have a choice of either splitting the channels. So remember, we have two channels, we have DAPI and we have actin. So I can either split them or I can show them together in one image. So let me show you what this looks like first of all. So let's say we don't split them. So then we get this super pretty picture. In this particular picture, the red represents the DAPI and green represents, of course, actin. Now let's say I wanted to show it in a split view. So again, I can carry this file into Fiji, and then I can click on split channels. And this is going to give me two individual images. One is the DAPI channel, while the other one is my actin channel. Of course, I could go back here and I could actually split the two channels from here as well. So if I have this image, I can go to Image, Color, Split Channels, and now you can see that this image, the composite image, has been split. But I'm just going to close this, and I'm going to work with these grayscaled images. So these are the split images from the get-go. So again, we have DAPI over here, we have actin over here, and you can see that there are quite a few eukaryotic cells here. Of course, this is a nucleus of a eukaryotic cell. And we can also appreciate the presence of the Salmonella bacteria. They're right over here. Okay. Now, the next thing I want you to kind of see is that the bacteria are very, very small and they're quite dim compared to the eukaryotic nuclei. And this is a little bit challenging because it's kind of hard to see them. So what can we do? Well, we need to enhance the brightness in this particular channel, in the DAPI channel. Okay, so let's do that first. So again, we go to, we select this file, we go to Image, Adjust, Brightness and Contrast, and now we can play with these parameters. So if I take this maximum and I bring it a little lower, you'll see right away that this image becomes much, much brighter. Now you'll note a couple of things happening here. The image is becoming brighter kind of everywhere, which means that the eukaryotic nuclei as well as the bacterial cells are becoming brighter. So this is something to note. Now, of course, if I want to see the bacterial cells clearly, I'll put the slider somewhere over here, and this sort of saturates these cells, and that's okay. This is something we just need to be aware of. The other thing I might want to do is actually I might want to adjust the minimum value as well, and that's because now that I brought this upper slider down, you can see that this is no longer black. To make it black, you just adjust the lower slider a little bit. And I encourage you to play with all of these parameters to see how this works. Now let's see what this would look like if I was to merge these two images right now. So I could go to Image, Color, Merge Channels. So C equals 0 is my DAPI channel. So let's say I want my DAPI to be in blue. I would put it right here. And C1 is my actin channel, which traditionally was red. So let's put it in the red channel. And this is what it's going to look like. So right away you can see that this is a pretty picture, but if you look at the bacterial cells right over here, it's very difficult to see them. They're still not bright enough. So I suggest we go back and continue enhancing our images. So let me just close this for a sec and let me reopen this file. That's kind of the unfortunate thing with ImageJ. You have to reopen the file all the time, or alternatively, you could duplicate your images. And you duplicate them by clicking, I believe it's a Control Shift D, or just Control D. You can check this out if this actually works for you. Okay, so we go to Image, Adjust, Contrast, and we can adjust a little bit to kind of see the image a little better, to see those bacterial cells a little better. And you'll note that what I'm doing now is I'm saturating the image much more. So I'm not going to see much detail in the eukaryotic nuclei, and that's because I really want to see those bacterial cells. Okay, so now it's much more saturated. And what I'm going to do next, so I'm actually going to saturate a bit even more, like that. Look at that, isn't that beautiful? So remember now what we want to do is we want to merge this picture with this picture. We want to merge these two channels because these are part of the same cell. This is the actin of those cells, and this is of course the DNA of the cells. Now before I'm going to do that, we worked on this image quite a bit, on this channel quite a bit, but we didn't really do anything to this channel. And what we can do here is we can work on the brightness and contrast a bit as well. So you can see that here it appears like this is true black color, but here it's not quite black, right? So let's see what we can do about it. So we can make it a bit darker there, and we can make the light um, elements of this picture, so the actual actin, a bit brighter. Okay, so this looks right away like a much better picture than it looked just a second ago. Okay, so just minor adjustments make a much prettier picture. Now going back to this thing, kind of still trying to figure out what would be the best parameters for this. Basically trying to make sure that we see all of these bacteria quite nicely. Now please note that the image would have looked much better if I actually took it with a C100 times objective with the oil lens, and I'll show you in a second what that would have looked like. Okay, so I think this is a pretty decent product from this particular lens. And so what I'm going to do now is I'm going to go to image adjust and image color and merge channels. Again, what I'm going to do now is I'm actually going to put the nucleus. Sorry, just one sec. I'm going to put the DNA into the green channel. So right over here, remember this is C0, so this is C0, channel 0. I'm going to put the actin into the red channel, and this is what we're going to get. Now, just for the sake of interest, I would like to show you what it would have looked like if I put it into blue and red channels. So again, merge blue, red. This is what it kind of looks like in this scenario. So in my personal opinion, it's a bit easier to see the contrast between green and red than it is between blue and red. So, it's very difficult to see those nuclei over here. So it's bacteria over here, but it's a bit easier to see them over here. Okay, so this is what these images would look like. Of course, you can continue processing this image, and I encourage you to continue playing with all the sliders and all the features. And eventually, what you should really do is export one or save one of these images as a TIFF file, export it into PowerPoint or into some kind of maybe Illustrator, whatever the software is wherever you make your figures. And then I also want you to zoom in on a particular portion and make it more visible. And it's really up to you whether you choose red and blue channels or green and red channels. It doesn't really matter. Just keep in mind that all of these colors are pseudo colors. These are not real colors, of course, not true colors. The next thing I would like to show you is the difference between acquiring an image with a 100 times objective and a 60 times objective. So here's an image that I acquired with a 100 times objective. So again, I'm going to split the channels to get us started, and show you what it looks like. So right away you can see that the cells look much bigger. So again, this is our actin and this is our DNA stain. So these are the nuclei for these particular cells, and all of these wonderful things over here, these are your little bacteria. So again, we're going to start off with our brightness and contrast. We're going to move the slider this way, remove this slider that way, and we end up with something that looks like this. Now what I'm going to do now is actually I'm going to duplicate, so I'm Control Shift D, and I'm going to get another one of these images, and you'll see soon why I wanted to do it. Now before I use that, I want to go to my actin and see what's happening here. So again, the image looks pretty decent, but I'm actually going to adjust this slider just a little bit so it looks a little more like this. And then I'm going to show you what it looks like when I merge them. And again, I'm going to put them into green and red channels because I believe it's a little easier to see the difference, unless of course you're colorblind and then you would use a CMYK altogether. to show the differences between the two channels. So again, I highly encourage you to have a look at that feature as well. So instead of RGB presenting everything in CMYK. So going back here, color merge. I'm going to put octane into red. So we're dealing with C equals 1, which is right over here. And the green is going to be my DNA, which is right here. And we get this image. So this looks like a beautiful picture right away. Okay, so this is this image. Now keep in mind again, it's sort of a little difficult to see this particular cell bacteria over here. However, it is quite easy to see this bacteria over here. Now, why did I put this image to the side? Well, I want to show you a little something a little different. I wanted to show this threshold here. So threshold again is something that they're going to highlight all the non-black pixels. So what we need to do now is we need to identify all the non-black pixels. So everything that's red in here is non-black. So you can see that we're actually missing here. Just one sec here. So what I'm going to do is I'm going to go back to my contrast. I'm going to apply it a little bit like this, just to make it a little brighter. Make it like this, and I'm going to click on apply. So now it saves the setting. So when I go to threshold, it might be a little easier for me to work with this. Okay, so this is what this looks like. Now I'm going to click on apply, and now you see that everything that was red became white. Now regardless of how dim this staining was and how bright this staining was, now they appear to be the same. So essentially everything that was not black has become completely white. Okay, it might be a little bit easier to work with this kind of image. Now what can I do with this image? Well, the first thing I can do is I can actually go ahead and show you what it would look like when I merge this particular image now with our octane. So it looks, oh, of course, they don't have the same color depth, just bear with me. So if you look at this one, image type, it's a 16-bit image, and this one is an 8-bit image. So we're just going to convert this one into a 16-bit image. And now we can merge the colors right over here. So red gets the octane, which is of course C1. Green gets this modified threshold image, and this is what we get. So what can you tell when you compare this image to this image? Well, right away you can see that this is not a true image. Of course, this is heavily modified, and we have to acknowledge that. This, of course, is also heavily modified, but not as heavily as this one. However, if you're only concerned about seeing where you have those little tiny bacteria, this is quite useful because it's very easy to see where the bacteria are. Okay, so for example, here it's very difficult to see this little bacteria over here, but this kind of analysis makes it much easier to see this. Now, in terms of the quality of the data, you lost quite a bit of data in performing this exercise. Okay, so it's very difficult to see, of course, how big this bacteria is. It's very difficult to do anything with this particular data, but nonetheless, it's a useful tool to be able to visualize those little tiny bacteria. And once again, I would like you to appreciate the difference between these images that were acquired with a 100 times oil objective and the previous image that was acquired with a 60 time objective. It was an air objective. So different kind of objectives, of course, give you different kind of resolutions. The next thing we would like to do is to use ImageJ to quantify the number of objects in a picture. Now remember that ImageJ doesn't really know what exactly it's quantifying. ImageJ quantifies things based on their size and shape. So what exactly do we want to quantify here? We want to quantify the number of nuclei and the number of bacteria in our field of view. So let me just drag this image into ImageJ. It opens right here. Of course, we have octane here, and we have DNA stain over here. In order to quantify the number of nuclei, we're going to use the DAPI channel, and in order to quantify the number of bacteria, we're also going to use the DAPI channel. And so we basically don't need this channel for this exercise. we're just going to close it for now. So how many nuclei do we have? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12-ish. Okay, so we have about 12 nuclei. Now, of course, you can count it manually. However, the point of this exercise is to learn how to count it using ImageJ. And you might be wondering, well, why would I do it? Well, in my past experiences, I've been looking at fields that have thousands of cells in them. And then you might have thousands of those images. And so if you want to quantify it, of course you can sit with a counter and quantify it, but it becomes a very daunting exercise. And so it's very convenient to use ImageJ to quantify those objects for us. So how do we do it? The first thing we're going to do is we're going to enhance this image just a little bit more so we can actually see the different features. So pull the slider a little bit, make it a bit darker. And I would like to show you first of all how to quantify those number of nuclei, right? So at this point, I'm actually going to duplicate this image, Ctrl-Shift-D, and that's because I want to have two of them so that once we've modified one and close it, we still have the original one still opened. So now we have this image. We can go to threshold and we can threshold it. And what I'm doing now is I'm quantifying the number of nuclei, right? So I'm selecting all the nuclei. Of course, it's also picking all of this bacteria, but that's not necessarily what I'm interested in at the moment. I will be interested in this when we quantify the number of bacteria, of course. So now that I've selected all this, we can click on apply, and it's going to convert this image into this black and white. Everything that was red that has been selected is now white. Everything that was black is now totally black. And now comes the fun part, quantification. If you go to analysis or analyze, you have this analyze particles features over here. And this is what you can use to quantify the number of objects. Remember, so each one of these things is an object. If each one of these nuclei is an object. And you see that one thing that we need to do is we need to identify what size the objects are. The other thing that we need to identify is the circularity of the objects, and this ranges from 0 to 1. And I encourage you to play with this. Clearly, the circularity of this is not the same as of this. However, for the sake of this exercise, we want to capture both. And so we're going to measure the circularity from 0 to 1. But when it comes to size, we actually want to define a certain size. Everything below that size, we don't want it to be counted. So how big is this nucleus? Well, we don't really know. So we're going to close this for a second. We're going to pick this elliptical selection feature, and we're going to quantify it like this, approximately. Okay, it doesn't have to be very accurate at this point. And now I want you to click on Control M. And what that is going to do is going to tell you how big this area is. So it's telling you that this area is 18,902. Okay, and this is in pixel square. Now let's take this little shape here and carry it over here, adjust everything. We're just basically going to measure a few of them to get a rough idea of how big these objects are. I'm going to drag it here as well. Maybe we, oops. Maybe we're not going to do this. Maybe I'm going to pick this shape, just to be a little more accurate. And now I'm going to again click on Control M, and so you get this idea. So this is around 13,000, this is around 19,000. So this is the kind of sizes that we are dealing with. So now we're going to go to Analyze Particles, and what we want to measure is something of this size. Okay, so maybe I'm going to set 6,000 to infinity. Okay, so everything's from 6,000 pixel square and bigger will be measured by my algorithm or by my counter. Click OK, and it's asking you if you want to save these three measurements. We don't really want to save them, and this is what we get. So what did ImageJ do? Well, ImageJ quantified all of these particles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so it captured all of these 11 particles. And this is pretty close because remember that we counted 12 manually. For some reason, it didn't count this. Maybe because there's a black pixel over there that kind of breaks the continuity of the red stain, maybe for some other reason. So again, you just adjust your parameters and that will ensure that it counts this as well. And this is kind of the point of this exercise, to learn how to use this counter. In a very similar way, we can also quantify the number of bacteria in this particular field of view. So we're going to close this one because we no longer need it. And we're going to get back to this image. Remember, this is the original image that I duplicated. So let's see what we can do with it. We can make it just a little brighter, so it's a bit easier maybe to see the various elements here. And now what we're going to do is we're going to threshold it once again. But now we're going to focus not on these big things, but rather on the little things. Okay, so this is doing a decent job. You can see that it highlighted all of these ones, but it's still missing these guys over here, and it's missing those guys over there as well. So maybe now it's a little better. Okay, so maybe somewhere in between. You know what, this looks like a good kind of compromise in between. So you can see that the lower I drag this, or the more I drag this slider to the left, the more of these features I see. But on the other hand, the bigger these guys become. And so right here, for example, if I remove this slider, you can see that you actually have a couple of bacteria over here. But when I drag the slider all the way down, you lose that information. Okay, so remember I told you that when you do this kind of analysis, you oftentimes lose some information. And you do have to compromise. You might not be able to capture all of the bacteria in addition to this particular, or in addition to being able to clearly distinguish between different bacteria over here. So a compromise that you have to do. But for now, we're just gonna highlight them maybe like this. Just give me a second here, maybe like this. So I think I'm happy with this. And I'm going to apply it. Now, what exactly do we want to quantify? What we want to quantify now is the number of bacteria. So we no longer want these big things, we want the little things, right? And so what I'm going to do now is I'm going to select my selection tool, and I'm going to measure how big these little things are. And again, you don't have to be supremely accurate here. You're just going to want to get an idea of how big these things are. Now, you don't want to quantify anything that's below about 5 pixels square in size, because that's typically just noise. But now we also don't want to quantify these large things, right? And so remember that we can measure them to kind of estimate how big they are. So 17,000, maybe this one is smaller, and maybe this one is a bit smaller. So I would say that you can quantify everything from maybe 5 or 7 pixels up to maybe 1000 pixels in size, and this will give you a fairly decent estimate of how many of these smaller objects you have. And so what we're going to do now is we're going to go to Analyze Particles, and we're going to select 5 to maybe 6, maybe 4,000. Also, our bacteria are very, very small, so it's not going to get up to here either. Click OK, don't save, and you see what it has done. It quantified all of those little things. Okay, and now of course you can once again play with the various parameters to optimize this particular quantification, but you can see that you're on the right track. You are able to use ImageJ to quantify both big things, such as the nuclei, and little things, such as your bacteria. And finally, depending on the instructions of this particular lab, you might want to compare the number of nuclei and the number of bacteria that you counted manually versus the number of bacteria and the number of nuclei that were counted by your ImageJ algorithms. You might want to compare them, maybe put them together into a table or into a graph bar of some sort, and then you might want to discuss it in your report. You can also, of course, discuss the limitations of this kind of ImageJ algorithm, and I kind of mentioned some of these limitations as I was talking about how we use it to quantify various objects in our fields of view. Of course, you can also talk about the power that this tool gives us. In other words, I don't need to sit and quantify or count many different cells. I can develop an algorithm that will automatically count the number of cells in my fields of view. And then what I can do is I can import an entire folder of images into ImageJ and apply this quantification algorithm to all of the images in this folder. And within minutes, I'll know exactly how many objects of a particular nature I have in my pool of pictures. And this brings us to the conclusion of this particular tutorial. Thank you all for tuning in and have a good day.